So, when you're talking about vectors in space, if so, if I want to plot a point, for example, in three-dimensional plane, how many of you have you plotted points in 3 dimensions before? Yeah, you have. Good. It's nothing special or anything. This is the x-axis over here. This is the y-axis, and this is the z-axis. So if I want to, for instance, plot the point 3, -2, 4 in 3 dimensions, I would come out here 1, 1, 2, 3. I'd go over 4 in the positive, back 2, sorry, in the positive, in the negative y direction. And then I'd go up 4 along this axis. So it's kind of hard to kind of see where that point would be, but hanging out somewhere up there. You see that? Okay. So it's x, y, z. Okay. Did I do what's wrong? So z is the up and down, okay? So x, positive y, positive z, okay? What?
Yeah, shouldn't Z be depth? Yeah.
No, that's the way they always, it doesn't really matter, but no, they go x, y, z, like that. Z is up and down. Okay, and so the distance formula, just like in geometry, if I want to find the distance to a point, you can find the distance to that point right there by using the distance formula in 3 dimensions, or the distance between 2 points. I'm sorry. Okay. And so all you do is you subtract the x's, you subtract the y's, you subtract the z's, you square them, you take the square root of it, and you find the answer. Okay, so in this case, the distance would be between those 2 points, 4 minus -1, and it doesn't really matter which order you subtract in since you're squaring them anyway. But 4 minus -1 is 5, right? Squared, and -2 minus 3 makes -5 squared, and plus, like that, and plus 5 minus 2 is 3 squared, and when you do all that, 25 plus 25, you get the square root of 59. Okay, is that hard? Easy, right? Okay, next thing, if you were to, what happens if I do this? Can I move this up? No. Can't do that. I still haven't figured out how I could just scroll down nicely without erasing everything. I have to call the reps. Okay, so the next thing, graph the point, -1, 3, 2, find the distance between, oh, we just did that, right? Find the position vector, P1, P2. All you do for that, just like you did before, that means the vector originating from 0, 0. So if I did have my x, y, z axis here, here, and not very good y axis, but there's an x, y, z axis. So if I want to find the position vector between those points, I just subtract. Okay, so you'd get v equals 4 minus -1, which is 5. Okay, and you could write it like this. 5, 6 minus 2 is 4. And 2 minus 3 is -1. Or the other way you could name that is 5i plus 4j minus k is in the z direction. Okay? And so to plot that point, you'd go out 5 this way, over 4 this way, and down 1, right? Or 2. And then you would draw a vector to that point. Vector to that point like down here. And it's kind of hard to see where it really is, but it's going down like that a little bit and in between those two. Okay? To find it, you add vectors just like you add them in, like you're adding two-dimensional vectors. So if I want to find, let's do v plus w. V plus w, that would be equal to 2 plus 3 in the I direction, 5i. 3j minus 4j would be minus j. And minus 2k plus 5 would be plus 3k. So if I add those two vectors together, you're going to end up with another vector that combines to make that. Subtracting works the same way. This you just multiply 3 times each of those. This one you would multiply 2 times v1 and 3 times w and then subtract them. And the magnitude, you have to take the square root of the square, the square root of the squares of the component. So the magnitude of v would look like 2 squared plus 3 squared plus negative 2 squared. Yes? Which is the square root of 4 plus 9 plus 4. What's that? 4 plus 9 plus 17? 17. Okay? And that's basically how long that vector is. Questions on that? Easy? This is easy, right? So far? And it doesn't get much harder. Unit vector, you do the same way. You divide by the magnitude of the vector. So if I want to find the unit vector, that's a vector with a length of 1 that is in the same direction. I need to divide by its magnitude. And in this case, the magnitude would be 4 plus 9 plus 36, right? Which is equal to 13 plus, oh, that's nice because that comes out to be 7, doesn't it? Okay? 13 plus 36 is 49, and the square root of 49 is 7. So that would be 2 over 7i minus 3 over 7j minus 6 over 7k. Okay? And that would be the unit vector that is the same direction as this vector, but has a magnitude of 1. Okay? Questions on that? Okay? All right. Dot products, you find exactly the same way as we've been doing. So you just times the i's, times the j's, and times the k's, and add them all together. And so if I want to do that, and it is commutative, so I could go v dot w or w dot v, get the same answer. So if I did that, I would get v dot w would be 10 minus 3 times plus 3 minus 9. 6 times minus 1 makes minus 6. So 1 minus 6 is negative 5. And this is just the same as this, right? It's a vector dotted by itself. Wait.
Where were all those numbers?
What? Where do these numbers come from? 2 times 5, negative 3 times 3, and 6 times negative 1. And then I add them again. Okay? V dot v looks the same as the magnitude of v, and that's just going to be, both of these are the same. It's just 4 plus 9 plus 36, and the square root of that. Okay? Which comes out to be 7. And that's the magnitude, and it's also v. Well, v dot v is what's inside, right? And the magnitude is the square root of what's inside. Okay? All right, so this would be v dot v, and this with the square root was 7 would be the magnitude of v dot v. Again, you could use this formula to find the cosine of an angle even in space. So if you have some vectors in space, I like drawing these three-dimensional plane. I think I'm pretty pretty good at this, okay? And so here's my three-dimensional plane, and you have one vector that is, let's change colors, one vector that is 2, out 2, back 3, up 6. So here's a vector sticking up here, vector u. And there's another vector that is out 2, over 5, down 1. So maybe down here. It's kind of hard to see, but you can kind of get the idea. And what you want to try to find is the angle between those two vectors, right? Because those vectors are, and so the total angle from, if I were to fold this on top of that, okay, even in 3 dimensions, can be found using this formula. So to do that, I'd go u dot v, which is 2 times 2, 4, what's that, negative 3 times 5, which is negative 15. 6 times negative 1, which is negative 6, over the magnitude of u, which is 4 plus 9 plus 6. Oh, look, it's 7 again, isn't it? Okay. 7 again. And this is 4 plus 9 plus 1, right? Oh, sorry. 4 plus 25, 29 plus 1, so that'd be square root of 30, right? On the bottom. And so that comes out to be 4 minus 15, negative 11 minus 6, negative 17 over 7 root of 30. And if you take the inverse cosine of that, no need to rationalize or anything because you're just plugging it into your calculator, of negative 17 over 7 root 30, you'll get an answer, right? And that answer is, clear. What did I say? Negative 17?
Over 7.
Oh, I could get so negative 17 divided by 7 second square root. Is that square root? Square root of 30. Close. I should have taken the cosine first. Second cosine. Second answer. Is that answer? Close. And I get that angle between those two vectors is 116. And it looks like it might just be 116, right? Or something like that. Okay? 116. Questions so far? Okay. And then the next thing is what happened? What happened to my nice? Where'd we go? I closed it. So it's okay. So next. So these are called the direction angles. And what the direction angles are the angles between the positive x, y, and z axis. And you just use this formula. So, so for example, let's try to draw the three-dimensional plane one more time. Go on this way, here, and here. So if I have some vector down here, negative 3i, which would be going backwards, it'd be going backwards 3, right 2, and down 6. So that's kind of hard to imagine, but maybe something like this. Okay, so say this is this. That's kind of hard because I'm going back, out, and down. So I'm not exactly sure that that's what it'll end up looking like in 3 dimensions, but we're going to pretend that it is. So the direction angles are the angles that they make with each axis, okay? So this angle here is the angle with the x-axis, so that's alpha, okay? And the angle between here and here, that's the angle with the y-axis, and that's beta. And the angle from here to here, that's the angle between the z-axis, and that's gamma, okay? Uh-oh, now I gotta try to draw gamma. I was getting better at it. Well, anyway, that's gamma, okay? And then the way you find that is just by, so for example, if I want to find angle alpha, it would be you would take the inverse cosine. Alpha is equal to the inverse cosine of A, which in this case is -3 over 9 plus 2. Oh, look, it's 7 again, isn't it? Isn't it? 9 plus 4 plus 36, it's 7. So if I take the inverse cosine of that, I would get that angle, which is, who's got a calculator? I don't want a negative cosine. What do you got there? Yeah, what's inverse cosine of -3/7? 115.4 degrees. Okay, so that's that angle. Even though it doesn't look like it, so I kind of drew my picture in the wrong spot. And then to find this angle, B, you take the inverse cosine of 2 over 7. Okay, so beta equals that. Okay, and gamma equals the inverse cosine. Sorry, put inverse cosine of -6 over 7. Okay?
Wait, why 2?
What?
Why 2 for B?
Why? Because
Oh, I see.
Okay.
Okay.
and -6 over here. Okay? And then the last little thing, is this is kind of like the Pythagorean theorem in 3D, or the identity, the Pythagorean identity in 3D. It's the cosine of a squared plus cosine of b squared equals the cosine of c squared. And this is kind of a tricky little problem. The vector v makes an angle pi over 3 with the positive x-axis, an angle beta equals pi over 3 with the positive y-axis, and an acute angle y with the positive z-axis. Find y. So the way that you would have to do that is you plug in. So you would go cosine of pi over 3 squared plus cosine, again, because beta is pi over 3, of pi over 3 squared plus cosine of gamma, I'm not very good at making gamma squared, I'm going to practice next week, 1. And anyone remember what the cosine pi over 3 is? 1/2. So this is 1/2 squared, which is 1/4, plus 1/4 e plus cosine of gamma squared equals 1. Okay? So that means that the cosine of gamma, I used to make these better, I don't know what happened, something like that, of gamma squared equals 1/4 plus 1/4 makes 1/2. Subtract that from 1, so that's equal to 1/2. So that means that the cosine of gamma is equal to the square root of 1/2. That says 1/2, which is also equal to cosine of gamma equals, that's equal to this 1 over the square root of 2, which is equal to the root of 2 over 2, which means, I should have plus or minus, but they say that it's makes an acute angle, okay, so I don't have to worry about the negative one, because the negative one, it would give me an obtuse angle. So what angle has a cosine of root of 2 over 2? Anyone remember? Nick? Pi over 4. So gamma equals pi over 4. Very good. So that's a tricky little problem, and it's nice because they made it so that the numbers worked out all good and stuff, you know. So that's how you do that. And this just says that the vector, vector in 3 dimensions. This is component form is equal to the magnitude of the vector times the cosine of that, the angle it makes with the x-axis times y, times the cosine angle that it makes with the y-axis times j, times the cosine angle that it makes with the z-axis times k. And you could rewrite it like that, and that's that, and you can try to do that. Okay? Do you have any questions?